All right, trig substitutions, aka trig subs. This is a fairly challenging topic, so much so that I wanted to remake my videos on this topic to hopefully make it make more sense to students. So at its core, trig substitutions are really just the same as U substitutions, but they feel kind of different from the student's perspective. So often people think about them as a completely different technique. But really, maybe it'll help to keep in the back of your head that really all you're going to do in this section is the exact same thing you did when you learned how to do U substitutions. The motivation for trig substitutions really comes from having multiple terms underneath a radical. So in this specific example, it's the square root of 9 minus x squared that's kind of causing the trouble, loosely speaking. The example I'll work out is a little bit more complicated than that, but even if we just consider the simpler example of the indefinite integral of the square root of 9 minus x squared, we wouldn't be able to easily figure out an antiderivative. You might be thinking, wait a minute, couldn't we just make this 9 minus x squared to the 1/2 power? I'd be like, yeah, sure, absolutely. Then you're like, couldn't you do some sort of power rule trick where we have 9 minus x squared to the, 3/2 power if we added one to this exponent, but then we'd have to make sure to put a 2/3 out in front. Wouldn't that kind of sort of work? I'd be like, well, almost, but not quite, because if you take the derivative of this thing, you bring the 3/2 down in front, that cancels out with the 2/3, you subtract 1 from the exponent, so you get 9 minus x squared to the 1/2 power, but then you're not done. You'd have to multiply by the derivative of the inside part. What I'm saying is that the derivative of 2/3 times 9 minus x squared to the 3/2 power is not just 9 minus x squared to the 1/2 power. There's an extra negative 2x in here from the chain rule, from the derivative of this inside function. So that doesn't work. And really the reason it doesn't work, what causes the trouble, is the nested functions, right? We got the 9 minus x squared underneath the square root sign, but we also have the square root sign. If only we could get rid of that square root, things would work out a lot nicer. And it turns out we can. First comment, the bad algebra comment. We cannot immediately cancel out the square root by taking the square root of the 9 and the square root of the x squared. What I'm saying is the square root of 9 minus x squared is most definitely not equal to 3 minus x. Because if it were equal to 3 minus x, well then 3 minus x squared should give us 9 minus x squared. But it doesn't, because 3 minus x squared you have to kind of FOIL, and you get 9 minus 6x, I guess plus x squared in this case. If algebra worked this way, where we could kind of distribute square roots over differences for the purpose of cancellation, this would be a much easier integral to take. But unfortunately, this doesn't work. So just like up in red up here, we kind of fail to find an easy way to take the antiderivative. So what are we going to do? Well, it turns out that what we're going to do is going to involve the Pythagorean identity. And that might be kind of surprising. Maybe you remember the Pythagorean identity from a trig class. Is that the sine squared of some angle plus the cosine squared of some angle always is equal to 1? This kind of comes from the fact that a squared plus b squared equals c squared in a right triangle, where a and b represent the length of the legs of the triangle and c represents the length of the hypotenuse. Anyways, maybe you remember this identity, and maybe you remember that the power of this identity comes from being able to rewrite it in equivalent forms. So for example, if I subtract sine squared from both sides of this equation, I get 1 minus sine squared of theta equals cosine squared theta. And for example, instead of subtracting sine squared from both sides of the equation, if I divided all three of these terms by sine squared, I'd get sine squared over sine squared, which is just 1, cosine squared over sine squared, which is cotangent squared, and 1 over sine squared, which is cosecant squared. So an equivalent form of this Pythagorean identity is that 1 plus cotangent squared of theta equals cosecant squared theta. And just like I could mess with this form by subtracting sine squared from both sides, I could mess with this form by, for example, subtracting 1 from both sides of the equation. I'd get cotangent squared equals cosecant squared minus 1. The point is just most people think about this as the Pythagorean identity, but really the Pythagorean identity is a little bit more flexible than what you see written in this blue box. Anyways, just some stuff I wanted to remind you of. And on the topic of reminding you of things that maybe you learned in a trig class, at one point you were probably able to rewrite all 6 of our trig functions in terms of sine and cosine. So maybe recall that the 6 trig functions are sine of theta, cosine of theta, tangent of theta, cosecant of theta, secant of theta, and cotangent of theta. But really, if you don't want to think about there being 6 different trig functions, we can think about there only being 2 trig functions, sine of theta and cosine of theta, because tangent of theta is really just sine of theta over cosine of theta, cosecant of theta is 1 over sine of theta, secant of theta is 1 over cosine of theta, and cotangent of theta is cosine of theta over sine of theta. If you write them in this order, this second column is just the reciprocal of this first column. One last thing to remind you of before we actually get to the process of trig substitutions is that each of these 6 trig functions have derivatives that you may have learned in a Calc 1 class. The derivative of sine of theta is equal to cosine of theta. The derivative of cosine of theta is equal to negative sine of theta. And then using those 2 facts in the quotient rule, we come up with the fact that the derivative of tangent of theta is equal to secant squared theta. The derivative of cosecant of theta is equal to negative cosecant of theta times cotangent of theta. The derivative of secant of theta is equal to secant of theta times tangent of theta. And finally, the derivative of cotangent of theta is equal to negative cosecant squared theta. For the rest of this video, I'm going to assume that you're comfortable with the Pythagorean identity and the stuff in pink and purple here. With all of that prerequisite knowledge, I can finally show you how to do trig substitutions. So again, back to our integral. We're trying to figure out the definite integral of the square root of 9 minus x squared divided by x squared. And the trick is going to be to do a u substitution, but it's going to feel a lot different. So instead of calling it a u substitution, I'm going to call it a theta substitution. So if we were doing a u substitution, we'd write something like let u equal some expression in terms of x, and then we take the derivative to get du over dx equals some expression in terms of x, and we'd multiply, loosely speaking, both sides of the equation by dx, and get du is equal to something dx. We'd have this expression for u and this expression for du, and we'd use these to rewrite this integral so that the letter x no longer appears anywhere. All these x's change into u's, and this dx changes into a du. All right, this is the method for a u substitution. What we're going to do is almost the exact same, except instead of choosing the letter u, I'm going to choose the letter theta. And the substitution that I'm going to do is not at all obvious. And for now, I just want you to trust me, but later on I'll show you how I came up with this substitution. We're going to let theta be equal to the arc sine of x over 3. At this stage, you probably think we take the derivative of both sides of this equation and come up with d theta over dx is equal to whatever the derivative of arc sine of x over 3 is equal to. And frankly, you could do that, but you don't want to, because the derivative of arc sine of something gets kind of messy, and it'll make the algebra really hard to do things this way. So even though the substitution that we're doing is letting theta be equal to the arc sine of x over 3, before we take the derivative of both sides, we're going to solve this equation for x. So maybe first we take the sine of both sides of the equation and get sine of theta is equal to x over 3. And then we multiply both sides of the equation by 3, and we get that x is equal to 3 sine of theta. Really, this is the line that's most like the u substitution that we're doing. But most books, including yours, completely omit this, and they're like, we're just going to do a substitution where x is equal to 3 sine of theta. Most books start right here, and I think that becomes kind of confusing for students. Because really this method is just a u substitution, and when you're doing a u substitution, you don't decide what x should be equal to, you decide what u should be equal to. So to make things analogous, we want to decide what theta should be equal to down here. It's arc sine of x over 3, but once we solve this equation for x, we get x is equal to 3 sine of theta. The stuff above this dotted line, think about it as optional. You're certainly welcome to start right here. Most books do. But maybe it's a little bit less confusing if I kind of show you the steps above the dotted line. We now know what x is equal to in terms of theta. So if you're thinking about this integral, we'll be able to get rid of this x and this x. But what about this dx? Well, when we change all the x's into thetas, we got to change dx into d theta. And we can do that by taking the derivative of both sides of this equation. We get dx over d theta is equal to 3 times cosine of theta. And if we multiply both sides of this equation, loosely speaking, by d theta, we would get dx is equal to 3 cosine of theta d theta. Much like with u substitutions, pretty quickly you'll go from this first line to this third line and completely omit this second line. Okay, so again, going back up to my integral, I now have the ability to get rid of all the x's and the ability to get rid of the dx by substituting in these different pieces. So that's exactly what I'm going to do. Instead of the integral being the square root of 9 minus x squared, all divided by x squared dx, my integral is going to become the square root of 9 minus something squared divided by something squared times something. And those somethings will be, well, instead of writing the letter x, I'm going to write 3 sine of theta. And instead of writing dx, I'm going to write 3 cosine of theta d theta. We're now done with our substitution. We took this integral that was written in terms of the variable x, and we rewrote it in terms of the variable theta. That's awesome. I mean, kind of. If you stare at this and you stare at this, you're probably like, I would much rather try to figure out this antiderivative than this antiderivative. It looks like we're just making things harder. I can see how you'd think that. However, this substitution that we chose was very intentional. It'll turn out that with this substitution, we will always be able to cancel out this square root sign. And remember, this square root sign is what was causing the trouble from the start. It's what was making it so hard to figure out the indefinite integral. So getting rid of that square root sign seems like a really good thing. The only bad news is it's going to really test your algebraic skills. So let's go through it slowly. We got this big fraction that we're taking the integral of. This 3 cosine of theta d theta in blue, I'm just going to leave it alone for now. The 3 sine of theta all squared, I'm going to rewrite as 9 sine squared theta, because what it means to square 3 sine of theta is 3 sine of theta times 3 sine of theta. So I can multiply the 3 and the 3 to get to the 9, and the sine of theta and the sine of theta to get sine squared theta. I can do something similar with these parentheses to change what's underneath the radical into 9 minus 9 sine squared theta. It's still not obvious how this is going to simplify, but you might notice that I have 9s in each of these terms underneath the radical. It'll turn out that this coefficient always will match up with the number that you have here. So you can always factor out whatever number you see in front of the sine squared from both of these terms. So in this case, I'm going to factor out a 9 to get the square root of 9 times 1 minus sine squared theta. I'm going to leave the bottom completely alone for now and continue to ignore this 3 cosine of theta d theta. Can you kind of see where this is going? If so, that's really impressive. What you have inside these parentheses, 1 minus sine squared theta, is really nice. What makes this radical problematic is that you have 2 different terms of things separated by plus and minus signs. This minus sign is what's causing all the trouble. I wish I could rewrite this as just one term. I wish 1 minus sine squared theta were equal to something else. Well, fortunately it is. 1 minus sine squared theta is equal to cosine squared theta thanks to our Pythagorean identity. So at this stage, we apply the Pythagorean identity to rewrite what's underneath the radical as 9 times cosine squared theta. That ends up being really important because now we can get rid of this square root. Now that there's only a single term underneath the radical, that term being 9 times cosine squared theta, we can apply that square root to each of the different factors in that term, the 9 and the cosine squared theta, to make this the square root of 9, aka 3, times the square root of cosine squared theta, which is just cosine of theta. That's a tiny bit of a lie. Technically, it's the absolute value of the cosine of theta, but you can ignore that technical detail for our work. Down in the denominator, I still have 9 over sine squared theta, and then I still have this 3 cosine of theta just hanging out over on the outside. Now that that square root's gone, things are going to work out really nicely. This 3 times this 3 gives me a 9, and that 9 divided by this 9 all cancel out. So what I'm left with is the cosine of theta times the cosine of theta, in other words, cosine squared theta, up on the top, and sine squared theta down on the bottom. What we ended up with doesn't look all that much similar than what we started out with here, but it's actually much better. This is something that we can integrate, whereas this is not something we can integrate until we apply this method. As you're starting to see, trig substitutions can be really challenging, so what I like to do is break them up into different steps. What we just saw is the first step, or the first part. And your goal in the first part is just to get rid of the square root sign. The only time you're going to use trig substitutions is when you have a radical, or a fractional exponent, which means the same thing. And the good news is the first part will always, more or less, follow the exact same steps that we did here with our theta substitution, our application of the Pythagorean identity, and canceling out the squared and the square root. When you get to the point where the square root's completely gone and you've simplified the integrand, you're done with part 1. There's still 2 more parts to go, but it's a good time to kind of pause and check in. Like, make sure that you follow all these different steps, make sure that you're okay to hear. Assuming you are, you can move on to part 2. And what you do in part 2 is you integrate. The whole reason we wanted to rewrite this into this form is because this is something we can take the antiderivative of. And you're like, all right, cool. What is it? Well, it's not super obvious what it is, but since we have cosine squared theta over sine squared theta, and we know that cosine of theta over sine of theta is equal to cotangent of theta, maybe we can use this fact to rewrite the integrand as cotangent squared theta. And you're like, yeah, that is nicer, but what's the antiderivative of cotangent squared theta? I don't remember that being the answer to any of the derivatives of my trig functions. Yeah, it's not, unfortunately. If it were secant squared, that would be awesome. If it were cosecant squared, that would be awesome, but it's not. It's cotangent squared. So what are we going to do about that? Well, fortunately, there's a relationship between cotangent squared and cosecant squared. Using this variant of my Pythagorean identity, I know that cotangent squared is always equal to cosecant squared of theta minus 1. So if I didn't want to integrate cotangent squared theta, I could instead integrate cosecant squared theta minus 1, because this is the exact same as this. Might look like things are getting worse, but they're not, because cosecant squared theta is something that we can deal with. We got the integral of a sum, which is just the sum of the integrals, meaning we need to figure out the antiderivative of cosecant squared theta, and then we need to figure out the antiderivative of negative 1. And fortunately, those are both things that we can do. First, the antiderivative of cosecant squared theta. Well, the derivative of cotangent of theta is equal to negative cosecant squared theta. Therefore, the derivative of negative cotangent of theta is equal to positive cosecant squared theta. And therefore, the antiderivative of cosecant squared theta is equal to negative cotangent of theta, technically plus c. What I'm saying is I can change this cosecant squared theta into negative cotangent of theta, and I can change this negative 1 into negative theta. Technically, I tack on a plus c, and I have my antiderivative. You don't have to, but it's worth pointing out that you could check that answer. The derivative, d over d theta, because theta is my variable, of negative cotangent of theta minus theta plus c would be the negative of the derivative of cotangent of theta minus the derivative of theta plus the derivative of some constant c. Well, let's see. The derivative of cotangent is negative cosecant squared. So I have the negative of negative cosecant squared. The derivative of my variable, just like d over dx of x is equal to 1, d over d theta of theta is equal to 1, and the derivative of a constant is always equal to 0. If I simplify a little bit, the negative of a negative is positive. I get cosecant squared theta minus 1. Because the derivative of this mess is cosecant squared theta minus 1, the antiderivative of cosecant squared theta minus 1 is this mess right here. We've gotten rid of the integral symbol. We've integrated. We're done with part 2. Moving on to part 3, the third and final part. What we figured out is that our integral is equal to negative cotangent of theta minus theta plus c. So it feels like we're done, but we're not really done because the original question was evaluating the integral of the square root of 9 minus x squared over x squared. Saying that the answer is negative cotangent of theta minus theta plus c doesn't make any sense at all because our variable up here is an x and our variable down here is a theta. Just like with u substitutions, we have to substitute back in. And you're like, yeah, but that's easy. From a couple pages ago, I remember that theta was equal to the arcsine of x over 3, which recall we immediately solved for x to get x is equal to 3 sine of theta. So all I gotta do is take this answer and change all of the thetas into arcsine of x over 3. Well, you could, but nobody writes the answer that way. If I change this theta and this theta into arcsine of x over 3, I'd get this expression, which is the right answer, but it's not simplified. Why is it not simplified? Because maybe you recall from a trig class that anytime you have an inverse trig function nested inside of a trig function, you can simplify. The cotangent of the arcsine of x over 3 is not simplified. How do you simplify? Well, there's this method of substitution. You say, I want to simplify the cotangent of the arcsine of x over 3. So you choose some letter. It doesn't matter what letter, any letter at all. When I teach trig, I typically choose the letter t. But here in calculus, I'm going to choose the letter theta instead. And we let theta be equal to whatever the inverse trig function is inside these parentheses. So in this case, arcsine of x over 3. Note that that's exactly the substitution that we had up here. If theta is equal to the arcsine of x over 3, then sine of theta is equal to x over 3. And if sine of theta is equal to x over 3, I can draw a right triangle, label theta in the picture, and use SOHCAHTOA, the SOH part of it, which tells me that the sine of an angle is equal to the length opposite that angle divided by the hypotenuse, O for opposite, H for hypotenuse. So if the sine of theta is x over 3, I label the opposite side with an x and the hypotenuse is a 3. I now have two sides of a right triangle labeled, which really means I know all three sides. This remaining side, I don't know, maybe we'll call it A or something, we can solve for. We know that this squared plus this squared must be equal to this squared from a squared plus b squared equals c squared. So therefore, a squared plus x squared must be equal to 9. And therefore, a squared is equal to 9 minus x squared. So a is equal to the square root of 9 minus x squared. Now that I have all three sides of this triangle labeled, I can simplify this original expression. And the reason I can do that is because the arcsine of x over 3 is exactly theta. I drew this picture by assuming theta was the arcsine of x over 3. So this expression, instead of thinking about it as the cotangent of the arcsine of x over 3, is really just the cotangent of theta. And the cotangent of theta I can express by using this triangle. I know from the TOA part of SOHCAHTOA that the tangent of theta would be opposite over adjacent. So because the cotangent is the reciprocal of the tangent, the cotangent of theta would be adjacent over opposite. What I'm saying is the cotangent of theta is the square root of 9 minus x squared divided by x. Since the cotangent of the arcsine of x over 3 is just the square root of 9 minus x squared over x, I can replace all of this stuff with all of this stuff. There's no simplification I can do over here on the arcsine of x over 3. I can only simplify when I have an inverse trig function nested inside of a trig function. So this is my answer, and it's completely simplified glory. The antiderivative of the square root of 9 minus x squared divided by x squared is the negative of the square root of 9 minus x squared over x minus the arcsine of x over 3 plus c. Wow. Okay, good news and bad news. The bad news is, as you've seen, this is really, really hard. Probably overwhelming the first time you see it. But the good news with trig subs is it's always kind of the same. These 3 steps that we did here, step 1, get rid of the square root, step 2, integrate, step 3, substitute back in, and simplify using this complicated method is always what you're going to end up doing when you do a trig sub problem. So even though it's a really challenging method, it's a very predictable method. And I think even if you're lost right now, when we see a few more examples of this, it'll make a lot more sense.